Hi everyone, so today I'm going to be discussing Green's theorem. So we have a problem here and it shows the integral of y dx minus x dy, where C is a circle with the center of the origin at the origin and a radius 4. So we can go ahead and solve this equation the normal way, not applying Green's theorem. So we can go ahead and parameterize x and y just because it is a circle. All right, so we're gonna do x and y. And so x is going to be r cosine theta, which in this case, our r is going to be 4. So we're going to write 4 cosine theta. And since we are parameterizing it, it's going to be in terms of t instead of theta. And then our y is going to be 4 sine t. And then we can go ahead and take the derivatives of both of these. With the first one being with respect to x and the other one being with respect to y. So our dx is going to be -4 sine t. And then our dy is going to be 4 cosine t. And then we know that it is a circle, so that means it's rotating from 0 to 2 pi. So our t is going to be from 0 to 2 pi. And then with all that, we can go ahead and plug this back into our integral. So we'll take the limits being 0 to 2 pi, and then we're going to put in our y, which is 4 sine t, with our dx, which is -4 sine t. Oops. Okay, and then subtracting it with our x, 4 cosine t, and then our dy, which is 4 cosine t. Okay, and then I'm going to go ahead and simplify this. So this simplifies to 16 sine squared. Ew. Oops. Okay. 16 sine squared t. And then the other one is going to be 16 cosine squared t dt. Dt right there. Okay. And so we can also simplify this down using trig identities. So this is going to end up being -16 dt, which if we go ahead and integrate it, it's going to be -16 t bounds. Okay, and then once you apply your bounds, it's going to end up as -32 pi as your final answer. Now, applying Green's theorem, I'm going to go scroll down here. So Green's theorem states that let C be a positively oriented piecewise smooth closed curve in a plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then our integral P dx plus Q dy is basically the same as our double integral over D of the partial of Q with respect to X subtracted by the partial of P with respect to Y dA, which is also going to be the same as our integral of the vector f over dr, where f is going to be p of I plus q of j. So let's go ahead and apply Green's theorem again with the problem. I've written the problem again down here. So we know that this is our P and this is our Q. And the reason why we can apply Green's theorem in this scenario is because our C is a smooth closed curve because it is a circle. And we know that P and Q are both continuous because we took their partials up here, and both these functions, -4 sine t and 4 cosine t, are both continuous. Okay, so let's go ahead and apply it. So if we take the partial of Q, oops. If we take the partial of Q with respect to X, we get -1. Yes, I don't know why that took me so long. Okay, and then we get the partial of P with respect to Y, we'll get 1. And so basically you're plugging them back into the formula. So let's see. you take -1 minus 1 dA, and that basically gives you -2 dA. Okay, so now let's go ahead and find the bounds for this and parameterize this. So this is, since it is a circle, we can go ahead and do the same thing. The only difference now is that you're going to do a double integral for Green's theorem to take into account the radius and the rotation. So we know our radius is 4. So we're going to do, okay, we're going to do from 0 to 4. And then we know that it's rotating from 0 to 2 pi. Okay, and then we're going to put 2 here. And then remember, for when we're parameterizing, we're going to also include r dr d theta. All right, and with that, we can basically integrate this. So starting off with this right here. So if we integrate -2r, we're going to get r squared, and then that -2 goes away and gives you -1. So we have this left over. Okay, and then that basically simplifies down to -16. Okay, and so now we have -16, the integral from 2 pi to 0 of -16 d theta. And if we integrate that, we're going to get -16 theta from 2 pi to 0. And you're going to end up with -32 pi. So both ways give you the same answer, as you can see. Green's theorem is just going to be faster and a quicker method for you, as long as the conditions are met that it is a positively oriented, smooth, piecewise, simply closed curve. And that is Green's theorem.